Okay, we're going to continue in section 1.4, which will complete chapter 1. And we left off last time proving a theorem that said a sequence converges if and only if each of its subsequences converges. And we proved that in that case, everything converged to the same limit, the sequence and all of its subsequences. Well, today we're going to prove another theorem that involves subsequences. But before we do that, I want to do a little bit of a review about negating a statement. One example I use frequently is if I simply say that all 100 congressional senators are men. It's not a true statement, but it is a statement. All senators are men. I'll go ahead and say, be more specific. I'll say all 100, not that that will affect this. I'm going to call capital S the set of senators and call capital M the set of men. So another way of saying this using an implication would be if X is a senator, then X is a man. Well, let's negate that sentence. One way of negating a sentence or a proposition is just by saying it is not the case that, and then repeat the statement. We don't want to do it that way. But the negation is, it is not the case that all 100 senators are men. So what's perhaps a nicer way of negating that? It should be easy if we look at the implication. This is like a P implies Q. It's only false under one circumstance. Remember, the P implies Q is only false when what? When that's true and that's false. So what would be the negation? You would say X is a member of S, a senator, but X is not a male, or not a man. So the way we write this symbolically is, one way of writing it is, instead of all senators are men, I'm going to write there exists an X in the set of senators. Yeah, where this is false, where X is not an element of capital M. In words, that just means there exists a female senator. All right, that's just the warm-up. Now, but part of it is that all, one way of writing that is for every X in S, X is also in M. I'm writing the same statement in many different ways. The only one that's the contradiction or the negation is this one. But these all say the same thing, the top three. So what we'll notice is when you're negating a statement that has a for every, this is for every or for each or for all, it's going to turn into a there exists. When you have a statement that has a there exists and you want to negate that statement, it's going to turn into a for all or for each. Okay, let's do a specific example that we're going to need in the proof of our next theorem. Okay, we know how to prove that a sequence converges to A. If in fact it does converge to A, we know how to prove it because we use the definition. All right, how to prove, or how do we prove that this sequence does not converge to A? So I'm going to write, how do we prove AN does not converge to A? All we need to do is negate the definition of what it means to converge. Sorry, I just noticed a whole bunch of cookies over there. They look great. Okay, so how do you think we're going to prove that? Well, let's write out what it means for AN to converge to A. And I'm going to use some the quantifiers again. For every epsilon greater than 0, there exists a capital N. Remember that? There exists a capital N in the set of natural numbers such that, well, I'm just going to put the whole thing in parentheses, for every n greater than or equal to n, the distance from an to a is less than epsilon. So using very few, or actually 0 full words, we've defined what it means for an to converge to a. For every epsilon greater than 0, there exists a capital N, which is going to be an index, such that for all n greater than or equal to this n, an minus the limit a is less than epsilon. All right, let's do the negation now. So an does not converge to a. All right, anybody want to give it a shot?
Well, would it be greater than epsilon?
Well, how about the very beginning? This says for every epsilon, something is true. We're going to negate this, so I'm going to have to start off with there's an epsilon where it's false. Okay, there exists an epsilon greater than 0. Remember what we do now? Instead of there exists an n, it's such that for every single n, it's going to fail. So for every capital N in the natural numbers, instead of for every negating this, instead of saying for every n greater than or equal to capital N, this is true, I'm just going to say there exists one of these n's where it's false. So there exists an n greater than or equal to capital N where an minus its limit a, the limit of the sequence, is greater than or equal to epsilon. So it's really quite simple. All of the for everys get turned into there exist. All of the there exists get turned into for every. And then, this was trivial enough to negate. Instead of less than epsilon, you just make it greater than or equal to epsilon. Any questions about that? Sometimes if you're reading this out loud and you want to read it in English, you have to throw some English words in there. I'd already mentioned, I believe, for every epsilon greater than 0, there's a capital N in the natural numbers, such that this is true. So I left out the such that. Down here we've got there exists an epsilon greater than 0, such that for every capital N in the natural numbers, this is true. All right, so we're going to use that in our next theorem, the proof of our next theorem. Theorem 115.